All right, I know it sounds like I'm bragging, but if it ain't bragging, if it's true, and it's true, I said all my stuff about these pictures here from our research and experiments with light, okay, and we saw these same particles that Fermilab saw. These are the light particles. Now they see them in just a big spray of debris, and they see these two and they don't realize they're supposed to be stuck together. Apparently they are supposed to be in what now they call gluons. Now this goes back to 2013. This was Don Lincoln had a bunch of articles about these different, well, this is right from his Fermilab point particle. These are the point part. This is the point particle, that's the fixed particle. So I sent him all this stuff and it didn't work out well at all. So that's the particles that we found. Now, those are the particles that make up everything that exists. Is the two little ones, the glowy one and the black one. The black one is all the matter, and the glowy one is all the energy. And again, this goes back to 2015. So here's, well, this goes back to 2014, let's say. And I got no response. They were really, Don and I don't get along, let me put it that way, at all. Very, very contentious. Now, because I'm not going to go there. So what I did is I ended up enrolling at the University of Geneva, which is in Switzerland, right next to CERN. I know they work together. And I took the course in particle physics and presented these things to the professors, and they said, no, you can't see this, it's impossible, la, 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 la. And I said, well, we're using CMOS. It's meant to see these things. And when they're coming through with this brilliance, CMOS has all amplifiers built into every pixel. So I explained to them, I said, we're doing this. Yeah, but they said, that doesn't matter. You can't use it because high energy, if it was this kind of high energy, it would destroy the pixel. And I said, well, we're using light. You guys are using big particles like this, so when they hit, they smash the photon, the pixels, and they just destroy the CMOS. They can't use it because it's like throwing hand grenades. We're using these. It's made for that. That's what it's made for. And you can see these really extreme luminosity, and because it's got amplifiers in every cell and you got all this special software, you can pump it up and see the particles. You can see them, there's no question. I see what they are. Exactly identical to these. These can get big or small. See how big that one is and small that one is? It depends upon which way it's going. It's going forward, so this one is bumping everybody else out of the way, and then sooner or later it'll get too big and it'll go loop, and I mean it goes quick, and they spin like this. They don't barrel roll. They spin this way according to the polarity of the Earth. Shown that a million times as well, and here's the proof of it. You see these particles are sitting straight, they're going that way, but they're up straight up and down. I believe that's quite obvious. All right, so it's the polarity of the Earth. They call them upspin and downspin, depending upon the glowy part, which is up or down. What else should I show you? Oh, light spins. It doesn't flap like a wave. This is what light does. And there's a whole batch of it coming down. It's not just one. The slit is here. And as it comes, you see it's like a drill bit. It literally drills. And it drills right through that slit. And this is the projection on the wall in the back. And see how perfectly aligned these particle waves are? Well, they're not waves. They're spins. They're exactly like this. It's just like you got a particle there. And it's nothing more than just like that. It's coming this way. And it goes bam, and it slides through. And then it bam, and it slides through. And then bam, and it slides through. And then on the back, the white ones are the ones that are getting through primarily. They don't like each other. They say, you stay in your line, I'll stay in my line. And they just set up these elegant, elegant, elegant patterns. Look at that. I mean, look at that closely. It floored me when I saw how perfectly, unbelievably perfect they are. Just incredible. And then they have, it must have something to do with the red, the distance of these bumps. And like green might be closer to, you know, I'm sure that would be the case. Green would be, you know, much closer, or it might even be further apart. I don't know. But I believe it's the color intensity creates the distance of the thickness of the waves, of the lines. No, they're not waves. There's no wave here. There is no wave. What they would say, it looks like a wave. Well, if you want to see a wave, that looks like a wave. That looks like a wave. But it's not. It's a spinner. It's spinning. I hope that makes sense to you. Okay, my friends, get ready. We're going to be talking about this event right here, where light seems to travel this way and that way at the same time. Physicists have mistakenly called this a possibility of time travel. If you can go backwards and go forward at the same time, obviously we can travel in space and time travel. No, you can't. It's bouncing back and squirting this way. It's only when light particles interact with matter that they get the bounce back this way, and they still spray forward. Same, exactly like this. Now, we're going to go into what they have to say about it, this big discovery they just made, and it all relates to dipole electron flood theory. They now have started to say, yeah, well, we can split photons. That's never been told before. They're supposed to be elemental particles, not able to be split. All right, I won't drag you through the whole thing, but this talks about my dipole electron flood theory. And it says impact on existing theories. Such a theory could challenge existing paradigms like quantum mechanics and relativity if it suggests a new mechanism for how electrons and other particles behave, which it does and it will. If verified, which it is, it would require revisions to many established physical models, requiring physicists and scientists to re-examine everything from particle physics to quantum field theory to cosmology, everything. Now listen to this. This is the conclusion. If Roger Spur's dipole electron flood theory were correct, it would introduce a paradigm shift in how we understand electron behavior, interactions, and the forces that govern the microscopic world. From revising the standard model, have to be changed, which I did. It's called dipole electron flood theory. Also altering quantum electrodynamics as understood now. Atomic and molecular physics changed. Even technological applications, how it's used, the implications would be vast. However, as of now, this theory remains speculative. Further experimental evidence would be needed to validate its claims. I have shown my experimental evidence. I expect the people that are making the claims about spending billions of dollars of our money to do things that I don't think are valuable at all should look at my research and say, well, Roger, it doesn't have any value, or, well, maybe we can work with it. But they have to look at it first, and that has not been done. Okay, this is the discussion in the scientific community, which I am not allowed to participate in, but here goes.
That challenges established norms. On the other hand, some critics argue that the term negative time might be misleading. German physicist Sabine has been a prominent critic, suggesting that the observed phenomenon is better understood as a phase shift in photons, rather than a reversal of time. According to her, calling it negative time risks over-sensationalizing what might be an artifact of measurement rather than a breakthrough in understanding time itself.
It's the photon bouncing back.
However, Angelo and Steinberg defend their terminology.
Well, they can say whatever they want, but time is not related to the photon. The photon is totally independent of time. It's so out of control now. They have no idea what they're doing in physics. There is no definitive proof photons can travel back in time. Recent quantum physics experiments have shown evidence of photons seemingly experiencing negative time. It's insanity. Listen to this. Photon splitting. By splitting a photon using special optical crystals, researchers have created a superposition where a single photon appears to travel both forward and backwards in time. That's insanity. I show you a splitting of photons. A photon's not supposed to split. It's supposed to be an elemental particle, have no mass, and unsplittable. It's basically a tiny singular particle that can't be split. Now they're talking about splitting them. Well, I've shown they can be split. I think they're working off of the things that I've shown, because nobody else can show this. Nobody, zero in the rest of the world has shown this other than me. And here, let me show you what they're still saying. ChatGPT, let's see. All right, you see it there? I put in, what is a photon made of? It says a photon is not made of matter in a traditional sense. Well, it is. It's made of matter. Everything is made of photons, and all matter is made of photons. Then they go on a quantum and electromagnetic radiation, no rest mass. That's insanity. Everything is made of photons, which are the two little particles, the black and the white. Now they say the energy of the photon and all this business. Well, let's come down to the bottom where it says right here. In short, a photon is massless, no mass to it whatsoever, particle that carries electromagnetic energy. It is not made of smaller components. So they're so lost. One guy says this, one guy says that. They're making a little thing so they can go get some funding. It's just a zoo in physics now, a real zoo. Okay, so here we got an issue right here, a photon being massless. It's not massless. The mass is dictated by the movement forward, basically. And it does have a resting mass of approximately 0.000585 atomic mass units, while it's just sitting here in this specific gravity. If we were up on the moon, it would have like a tenth of that or whatever. If we were on Jupiter, it would weigh 20 pounds. These are the things. It depends where you are, how much gravity you have, because that photon is pulled to gravitational forces, which is the dark matter that I have shown, which is nothing more than an accumulation of particles of light, and the dark matter goes to the center, as I have shown. Okay, here's the current claims they're making. Listen to this. Now, this just came out a couple of days ago. New type of magnetism. A new type of magnetism was discovered that could make electronics 1,000 times faster. Well, let's see what they have to say about this new type of magnetism. Altermagnetism. It means it's magnetic in one way and then all of a sudden it alters. Well, let's look into that. It's a newly imaged class of magnetism. Well, let's see what they show here. You see how they're showing these fields shifting and twisting around in a circle? Basically, that's what happens in a magnetic field. You have this. Now, there's a device where you can turn that magnetic field off just by changing the way the arrows go against each other. Instead of having a regular magnetic suck, it twists them so that they just turn around and they just fall off. And I'll show you that device. This has been known forever. These are the kind of things they're making, these little special little things. Research findings, potential impacts, magnets consist of magnetic moments that point anti-parallel to their neighbors. All they do is twist them so that they call it anti-parallel. Let me show you how it works. Okay, this is really cool. This guy's good. This is Action Lab short. And he's got a permanent magnet. I mean, it is a tough magnet. And all you got to do, there's a little switch on top. You turn it, and the fields go like this. Instead of going this way, they turn this way, and it just falls off. And that's what he's going to do. Watch.
This is a permanent magnet. This is not an electromagnet. So right now it's on, and it can easily pick up these still pieces of metal here. But then watch what happens when I turn it off. They just drop off like nothing, and it can't even come close to picking them up again. And I literally cannot pull this off. It is locked on there. But luckily I can just turn it off and it drops off like nothing. How is this turning a permanent magnet off and on again? This actually works by switching the direction of the two permanent magnets surrounded by some steel. When both poles of the magnet are the same way, the mag switch is on. But when one of the magnets flips 180 degrees, it short circuits the magnetic field so it can't escape the steel and the mag switch is off. So the inside...
Basically, it's hard to, looking at this, it's very confusing to my mind. Think of it this way. When the magnets are coming together, they're dragging each other together and they're entwined with their particles. And that's called a strong nuclear force. When you turn one of these magnets like this way, the other one just falls that way and everything just falls apart. It's the way the fields interact with each other, basically, is what the story is here. Okay, this is going to be fun. I looked at this 10 years ago, this was done, and I understand what's going on here, I think. So we're going to go into this complete video. It's only 5 minutes long, but it shows some unbelievable interactions with these charged particles in space, in a vacuum chamber, creating a literal black hole. When they saw it, they said, during the experiment, we contacted the Earth guys who couldn't believe it either. One of the guys from Max Planck locked himself in his office for 3 weeks. He freaked out. This is nothing like they expected. They've been working their whole lives making up all these stories, how this is going to happen. We're going to see a lattice like this, this, and this, and this, and this, and this, and everybody's going to keep its own position, and everybody's going to find particle everywhere. They know exactly what's going to happen. Then this happened. They go, whoa. So I obviously jumped in on this because I understand what's going on here, I think. I'm going to explain to you. So let's get started because this is going to go deep. They're talking now about light hitting something and going backwards and forwards at the same time. They just don't understand dipole electron flood theory. And without that, you're done. Okay, what I want you to pay attention to here is the details. They're saying the time observed, negative time, has been observed. Scientists discover time can go backwards. Here's their evidence for time going backwards. They shoot light at a medium something. They hit something. And they see light going this way, but they see light going this way too. It's going both ways at the same time. So they say that light is going backwards in time while this light is going forwards in time. I say that's basically insanity. Light has absolutely nothing to do with time, and it slows down as it goes forward. This is strictly bounce. That's bounce backwards. I show this very, very clearly. We shot a laser light into a medium, which happened to be a Venturi, and they show it basically the same thing. They're putting something in the middle of this so that it's restricted. We used a couple of different pins and did basically the same thing. And it might have gone around the pins, I don't know. But it came out like this, like crazy, and it came back like that, like crazy, and here it is. Here it is, my friends. What are you looking at? Well, that's the pulsed red laser. And light is a particle, I'll show you in a second, very, very clear. And as it spins forward very, very fast, it bangs into itself because of the reverse. Remember they say it goes both directions? Well, it does. It's hitting here so hard that it bounces back, and it bounces back so hard that it lights everybody up. This is a subatomic nuclear explosion. Anybody want to argue with me? I'd love to have them argue with me. We started with light particles which were fused together. They broke apart here, that's fission. They came back to here, it's fusion. In the middle is raw electronic energy. Electrons, the same thing as electricity, the same thing as static lightning. There's no weight to it, but it has a hell of a lot of energy. And you can see it's accelerated from this field. Now that field was a fairly small field when it started. that field was like this. All right, it's just starting to accelerate. Otherwise, you wouldn't even see it. You see, there's fields up in here. You don't see them. Why don't you see them? Why do you see this one? Because it's directly in line with the Venturi, and the Venturi is accelerating it. You see it? That's the only one you see. But they're all over here. The same fields, just like this. There's here and here and here and here and here, here and here and here and here. And this is the proof. There they are right there. Same as this. I don't see them. Do you? I don't see them here. Don't see them here. The only reason you see them here is because this is so violently exploding in every direction. So they're right. It goes forward, it goes backwards, extreme amounts of light. And that's the only reason the field tip illuminates. Light is a particle, and these are the Higgs fields coming out. This would be like looking straight in to the Venturi, like looking straight into this way. So there's a proportion from here to here, there's nothing at all. And out here is the Higgs fields start combining with the black. And I'll show you that in a second. And this is the particle that is the one, that's the only one like this that there is, that I've seen. And I've seen more of these particles than anybody at CERN, I can guarantee you. And that was the result of this, I believe, particle right here. You see what you're looking at there? This is coming out at us. All right, so we're looking right into the Venturi, and it's coming out. And you see these little white fields, these little white spritzes? You saw those little white zip, 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 and they're banging into these particles and turning into fields. Higgs fields. Those are Higgs fields. So between here and about here is just nothing but white. And then this is at the edges, it starts banging into them. But right about here, it's going to pow, and they'll all be lit up like a Christmas tree. All those little fields. And this is that little one. You see here? I know exactly what happened there, and I will explain it to a physicist that's interested, if one ever comes along. Now, I've shown you the particle. I don't know what I've shown you, to be honest with you. I got interrupted a couple times, and I've been working on 2 or 3 projects, and I'm working with some Russian guys that are interested in all kinds of stuff. They seem to be interested. It's just, I don't know. I just don't know what to think about American scientists. I really don't. It's been it's just a system of denial. I call it not science, it's deniance. Now, this is the red, this is the green. 2 different energy levels, quite obviously. Turning these into barrel rolls. I know I talked about this. And I don't know if it was on this video or not, but obviously I did. And again, this is banging and they're just shooting both ways. Exactly identical to what I just showed you. Precisely the same. And not only that, it is fission, where the black broke away from the white, and it is fusion when it came back together, and that's a subatomic nuclear explosion, and it's fission, fusion, acceleration of light, proving that light is a particle, because you got green, the same identical particle as the red, and these are the strong nuclear force, because this is in the nucleus. It's light, but light makes up the protons, which is the nucleus. So this is nuclear, but you can call it light. Electricity is nuclear too. I mean, electric particles are gluons. And a gluon, a gluon is heat. That's all it is heat. It's not really electricity. A gluon is heat. Electricity is just the white. That's the one that makes boom, it'll push through anything to get to the black. And it doesn't matter, it wants to get to Earth. Earth is a ground. Earth is literally dark matter mass. You're standing on dark matter. They say we can't find any of the matter in the universe, hardly. There's almost no matter. Well, what are you standing on? We're standing on matter. Light is the energy portion, the glowy part, and it can separate. I just never realized it could happen. But that's the green one, the red one, they're all the same. The blue one's the same. You can't really see the blue too well. But you can see the red perfectly. There's the red right there. All right? And again, they're polarized towards the Earth. And some of them are this way flat, and some of them are this way, but they're never going to be this way. Except for the one we did that double experiment here. This is the only time you're ever going to see them other than spinning like this, straight up and down to the Earth, is these barrel rollers, because it's just, this is going much faster than that. Boom, and knocks it, spinning like a barrel roll. I believe you can see that quite clearly. And then, of course, the green reconcusses way out there. So this is pretty clear stuff. Oh, you can't see these with a cell phone. You can't see these with CMOS. Absolutely, you can. No question whatsoever. They're using it right now at CERN. They upgraded to be able to use CMOS. They couldn't use it before because they were using big particles like this, which when they hit the CMOS, it had hit like that and it would destroy the CMOS. We were using light particles. Well, we used light particles. They didn't damage it. CMOS is made to see these. And when they're at high energy like this, it can see them very well. People, well, CERN doing the same thing, so yell at CERN, don't yell at me. I'm telling you, I'm not kidding you. This is almost it for dipole electron flood theory. We know these are the two particles, the smallest ones. They just never knew that they added together to make everything. They are called the smallest stable particles. They're one of each of these. Together, they are a dipole. And I call it atomic vapor. It's the vapor of everything, and it condenses just like water condenses from atomic moisture. Now, heat is nothing more than these two. That's all it is. It moves in and floods in and has weight, and it heats something up, and it actually increases the weight of things because it does have a weight, and it weighs approximately, 1,840 of these particles make one proton. So they're very tiny weight, but they flood in as heat. So that's whatever they flood into. Like if they flooded into Caesar here, he would get heavier. And as it went out to go somewhere else, it wanted those electrons, he'd get lighter. And it's like filling up a balloon, and then you get in an area where it's too pressurized, it'll vaporize some of it out. A proton is 1,840 or so of these two particles together. Like this is two particles. So this would be 920 or so of these photons. Now, the proton core is the dark matter. It's right in the center. It's dark matter is in the center, but it's all kinds of particles around it. It's not just one big dark matter and a couple of little electrons. It's completely saturated with electrons. That's the primary difference. That's what they missed. All right, so the dark is fixed size. All right, here's what it is. The proton core is the dark matter. That's what's inside every single proton. It's the dark matter. And the dark matter attracts the white, so the white coats it like a coating, like a frosting around it. The dark is the fixed matter size and the mass inside of it. So it gives this proton a mass, a weight. All right, and it's stable at approximately 1840. But you can go a few less and a few over, and it's still going to be semi-stable. But once you hit a certain point, it falls apart. And then they can rest. Mass is here. It's just the two reds and the two blacks. And, like no no glow at all if it's not moving whatsoever. When it's moving, it's banging into things, and the leading moving glowy part makes everything in front of it glow, like you can see right there. All right, comes through and makes everything in front of you. Get out of the way, get out of the way, get out of the way. That's what it's doing. Basically, that's what it's doing. If it could talk. But I haven't seen one talk yet. Although Rod did say he thought he had heard some clicking away, you know, which is what you could hear, because this right here, that's what's called a whistler wave. You see it out here? That's not supposed to be there. That's in the audible range. All right, that's way down here, in the audible range. We're supposed to be up here with these really squishy little waves. But this is banging here, and this is now you have strictly magnetic pulses. There's no mass to this, no mass whatsoever. The white is banging away ahead of it. So they call that a whistler wave because it makes a sound. And you know what, I suppose I should show you. Because I have a video showing an atomic explosion, which is this. And instantaneously, you're way out here and you're, which is this coming by you, was the sound. Moving at a very, very incredible speed, because it's the light, but it's this part of the light. Then the other part of the light comes and burns the house up, and then the black comes and knocks the house over. I've shown it a million times, but I'm going to show it another time now, because you got to see it and you got to understand it, and we got to change the way we're doing things here. It's not right. We got to look at this. If it's right, it's right. If it's wrong, it's wrong. But if it doesn't get looked at, you never know which way to go with this. And if we can get free energy, I think we can. And I showed you this, I'm sure, but if I didn't, this is it. I think we can get it right here by using it. Very, very simple. Carry it around in a little lunchbox. You shine a laser, pulse laser, through Venturis and pick up just the white, because that's all that's coming through. Just like they're doing at CERN. This is what they want to do. They're just not doing it the way as elegantly as we did. We shine the light through here, came through the white with no energy at all, low energy. Low energy. See, low energy came through. Then it created high energy. Well, what does it mean, low to high? That means you increase your energy. We didn't do anything. It came through. We didn't add any extra energy to it. It came through the Venturi. It went from low up to high. That's free energy. And it kept the muons back. See, the backtrack of the muons. They banged and they couldn't get through. But the white was squished through, which is precisely what I showed you. The black can't get through, and the white goes slamming through down into our battery stack, or just plug right into it and just walk down the street. Right there. No pollution, no danger, no radiation. Totally safe and cheap. You know, the particles, I mean, the parts are off the shelf and cheap as hell. Now, will it work? I don't know. I think it will. Because all you want is the white, and that's all you're going to get. You put a harvester right there before it hits back to the black where it wants to be. It wants to be attached to the black. So if you put from the white and you run it down through your batteries and all that stuff, it'll go through your motors and make them run and all that to get back to the other side, which is the black. It wants to get the ground. It's called a floating ground. You walk around with that all day long and it just work fine, if it works. And they say, that's what they say, energy of the neutrinos, which is the electron showers. All right, physics of electron showers. Electron showers is what I showed you, the white. At the end, where it says the energy of the neutrinos is a few 100 billion electron volts to a few trillion electron volts. Now, you're starting out In their case, they were proton-to-proton collisions. We don't need that. We use photon collisions. Okay, here's going to be some fun for you. What I want you to do is to figure this out for me. We've got the laser, and that takes a certain amount of energy, and that's in joules of energy. All right, so to convert electron volts to joules, you use this relationship. All right, 1 electron volt equals this. Now, here's electron 1, there's 1,000, there's 1,000,000, there's a billion, and then you go up into trillions. Now, the electron showers are way up in the high numbers of billions into trillions. Now, I believe we're starting with high numbers of millions of electron volts, but once you jump up, you're jumping up into a factor that increases it exponentially. If you're starting out with millions and you end up with trillions, that's free energy. Now, I want somebody to do some calculations on this. All right, so we're starting out with what does a laser take to run, and how many, joules would it take, how many watts, and you do all the conversions and figure out if it takes 5 watts to run this little laser, and we get out of it whatever the increase is going to be. And I showed you what the factors are, and they're over here, and these are the factors. All right, we created out of that little laser, that little bitty laser, we created these electron showers. Now, if we can get physics of electron showers, if we can get them up into a few 100 billion volts, electron volts, that's still a few 100 billion, which is on a low end because of the red laser. But if we did them on the high end, we would, with the blue lasers and all kinds of fancy stuff, we should be able to get trillions. That's a ton of extra energy. So what I want somebody to do is tell me how much energy does it take in giga electron volts or mega electron volts to run a small laser, and how much does it take for each different types of lasers, because I'm sure it's going to take more energy for the higher energy lasers. To make the laser laze, it's going to take energy. How much does it take? If it takes 50 giga electron volts and we get back 500, well, that's 10 times. That's a ton of energy. You should be able to carry it around. I mean, these things are not big to create generate electricity. These little tiny, you can get a little tiny battery charge this big. So you're not talking about a lot of room. Once you turn it with the laser and you split it, there's got no weight to it either. So you're not adding any weight, you're not doing anything. You just turn it on and you use the electricity, if it works. That's the key, if it works. But for the money they have spent, and to overlook this for 10 years does not make sense to me. So I know I'm only using a couple of, I don't even think it takes a 9 volt. The laser that we use is right here, hold on. And the cell phone we use is right here. There's just some Samsung Galaxy S3. The 2012 worked fabulously, absolutely fabulous. And I think Rod was using a lot of times the selfie side, right down there, taking through. He put it right into the thing. I don't know, but this is the laser. I guess it's got a whatever it is. It's got a tiny little battery in there, so we're not powering this thing with some kind of big exotic power. With 2 little batteries. How much energy, and this thing run for a bazillion years on those 2 little batteries, so we're not talking about a lot of input power. And if we can get a ton of output power, well, I think we'll be in good shape. And we can see what's coming out of there is just fabulously amazing amount of energy. Just completely white. That's all it is white. Okay, my friends, Happy New Year, and I hope in the new year we can all see the light. And not only that, we can enlighten our past and maybe have a good time in our eternity. But we have to understand reality before any of those things can happen. Happy New Year. I love you all.